Okay, hello again. So we're going to finish up the last couple problems from that webassign, and I forgot something on the last one. If you're wondering about part C to number 6, that was on the other side of my sheet, and I just missed it. So for that letter C for number 6, the block's got some kinetic energy, and that gets sort of used up or dissipated by the energy that goes into the spring and some friction. So the kinetic energy of the block is just the sum of both of those. And I think that's what they're asking you for. No, you just need to use this total to then set equal to mv squared over 2 to solve for v. So you need to use this fact to then get the speed of the block. For number 7, we've got a graph kind of like that. And I'm not going to put in all the numbers, but I am going to use some of the numbers that came with my version, the randomized numbers, so that you can hopefully at least get an idea how to do some of this. For starters, they tell you that okay, it's a 1 kilogram particle, and they say if it's released here, it's got a certain speed. So this particle definitely, it's moving. You've got the mass of the particle. They say it's got a certain speed, so you can definitely calculate the kinetic energy of the particle. If it's here, we can also go across the graph, and at least for my numbers, that says that it's 20 more joules. So we can get a grand total, some number, for the total amount of energy that this particle has. That's kind of like, say, how much money you have. Maybe you've got money in a savings account and you've got some cash. That's the total amount of money that you have. That's the total amount there. And it can't get any more. Physics is not like government finances where you can just borrow more and more and more money. You've got a certain amount of energy here, and that's it. So then for letters A and B, they ask about if the particle can get to a certain spot. Well, at least for letter A, they're asking about whatever the energy is up there. And so if you look from your particular graph, it's got a certain amount of energy there. And let's just pretend that my number was, say, 40 joules. Well, if I've only got 40 joules, and this one has an energy of 45 joules, I can never get up there. So the answer in that particular case would be no. So you're going to end up being somewhere else. You will not get to that position. You just don't have enough energy. It's kind of like the bowling ball swinging in the classroom. You start at a certain height, it's never going to get higher than that because it's only got so much energy to begin with. And I'll sort of get back to the end of letter A in a second. For letter B, they want to know the magnitude and direction of the force. So the important thing to know that force equals negative du dx, which is fancy calculus terminology for the force is just the negative slope of this kind of graph. So if you can get the slope of that section, you will have something that will say something like joules per meter. So then that tells you every meter you go, how many joules of energy does it take, or sort of does it use up. So if you've got a certain amount of energy here, you can figure out, again, from that ratio, from that slope, how far do you go until you've used up all your energy. And it's pretty much the same things for letters C and D. I think they're just asking about the other side. Okay, so those are kind of the important points. You got to look at the total amount of energy. You definitely have to look at the slope, which is like saying F equals negative du dx. From that slope, you can figure out how far it gets to if it does not indeed get to certain points. Erasing that. For number 8, they give us a graph that looks something kind of like that. And if you remember the same thing that we just mentioned, for an energy versus position graph, the force is the negative slope. If you kind of zoom in on or focus on say a section like that and a section like that, you see they're pretty much a straight line. That was done on purpose. And so if you can get the slope there and the slope there, and this part just kind of like connects the two smoothly, you can change this energy graph into a force graph. And here we clearly have a very negative slope. Force is the negative of that slope, so I'm going to put a positive up here. And here we clearly have a less, but a positive slope, so I'm going to put a negative there. And I'm just going to kind of connect those two with sort of a curviness and get something like that. Let me check to make sure that looks good. Yeah, that does look good. And for the last graph that we'll try and fit in here, this won't be the best in the world, they ask you to make a graph of k as a function of x. Kinetic energy. Yes, and they also say the total energy of the system is 4 joules. So if you want to say, I don't know how to draw this graph, like where do I start? It's always a good idea for graphs to just start at particular points. Sometimes it's very difficult to just go from there to there all in one sort of swoop and just get the answer. So instead for this one, even though I don't have a ton of room, let's say I make a very simple sort of looking chart where I pick a couple of x positions. And for those, if our total amount of energy is composed of kinetic and potential, well then I know my total is 4. At 0, I got to go back and look at my graph. At 0, if you look at the original graph here, I know I have 4 joules of potential. Well, if 4 joules is the total and I've got 4 joules of potential, that must leave me with 0 for kinetic. It's like a little column. And so we should indeed have 0 there. If I look at where the 1 is, got to go back and look at the graph, that looks like about 1 joule. And so this one's got to be a 3. So if you do that a few times, basically plot those points there, you'll end up getting something that kind of looks like that. And I believe that's the very end of number 8. Yeah. So Emily's bothering me now, so I'm going to go talk to her. So keep working on the webassign.